Test time adaptation for weakly supervised salient object detection. In salient object detection, we are given an input image and the task is to extract the most prominent object. We can train CNN on training data to perform this task. Such CNN is called base CNN. The trained CNN may overfit to the training data, producing bad results on the given test image. It is common to apply dense CRF post-processing, and it does help to clean isolated noisy pixels like these ones here, but it's unable to correct large erroneous regions like this one. We propose test time adaptation to adapt base CNN to a given test image. Adaptation is performed by training the base CNN for a few epochs on a small dataset constructed from just the test image. Adapted CNN is more likely to produce a satisfactory result as it's able to change large regions due to learning a better model for the test image. Test time adaptation is an extreme approach to deal with overfitting. The idea is that the test image is the most similar image to the test data, so we train on the test image itself. The main difficulty of test time adaptation is that there is no ground truth during test time to use with loss functions such as cross entropy. Thus, test time adaptation is not widely used. However, for the task of salient object detection, there are multiple approaches which are trained without pixel-precise ground truth, just from the images containing salient objects. Such training is called image-level supervision. We adapt a prior approach from CCV 2020 called regularized loss, as it is particularly suitable for test time adaptation. Our approach is the first approach for salient object detection test time adaptation. In the regularized loss approach, the main component of the loss function is CRF loss. CRF models are widely used in classical computer vision to model the likely object shapes. A shape is likely according to CRF model if it is well aligned with image edges, as object boundaries tend to cause image edges. The main idea is to use standard segmentation CNN and supervise it with CRF loss. For example, this output is likely just noise, and thus it has large CRF loss. This output is not noisy, but the object does not align with image edges. Thus, CRF loss is also large. For this output, the object is well aligned with image edges, so CRF loss is small. For test time training, we design a suitable regularized loss function. It consists of three components. The first component is CRF loss. As explained on the previous slide, CRF loss encourages object boundaries to overlap with image intensity edges. It cannot be used by itself, however, since the optimal solution for CRF loss is either everything assigned to the foreground or everything assigned to the background. To avoid the solution where everything is assigned to the foreground, we use positional loss. Positional loss encourages the image border to be assigned to the background. This is a reasonable loss as image border usually belongs to the background. To avoid the solution where everything is assigned to the background, we have volumetric loss, which penalizes objects which are too small. In particular, we penalize objects which are smaller than 15% of the image in size. We set the weight of the boundary loss to 1, as it is the least important component and in fact can be removed without too much harm. The relative weight between the CRF and volumetric loss are very important. If CRF loss weight is too large, everything gets assigned to the background, giving us an empty solution. If CRF loss weight is too small, we will get solutions which do not follow image edges very well. Thus, it's important to assign an appropriate CRF loss weight, and the best weight is image dependent. We develop an algorithm for estimating CRF loss weight for each particular test image. This is done by ensuring that CRF loss weight is large, but not so large as to get an empty solution. For test time adaptation, we create a small dataset consisting of 16 images from the test image by random horizontal flips and up, down, and left-right shifts. For our base CNN, we use the regularized approach from CCV 2020. This approach is image-level supervised, which means it is trained on Salient dataset, but without any other annotation or supervisory signal. Thus, our overall approach is image-level supervised. We compare our test time adaptation approach to a large number of prior works, which are also image-level supervised methods. The comparison is on 6 different saliency datasets. We use 4 standard metrics for saliency detection. With the exception of 2 cases, we outperform all prior work on all datasets and for all metrics. Our approach is in the last column, and almost all numbers are in bold. We also compare our work to prior work which uses stronger forms of weak supervision. In particular, we compare to method which uses boxes, another method that uses scribbles, and yet another method that also uses scribbles. Boxes and scribbles provide much stronger form of weak supervision. The user annotates a box around salient object or annotates some pixels present in the salient object and the background. Our approach is better, always better than the first 2 box and scribble supervised approaches, and is also better than the second scribble supervised approach for most data sets and metrics. Here we provide visual comparison of our method to 2 prior works that use stronger form of supervision, namely scribbles. Notice that we extract object shapes better, and this is due to directly using CRF laws for supervision. We presented the first test time adaptation approach for salient object detection. We show that the regularized loss function is particularly appropriate for test time adaptation. Our method has simple and intuitive loss function. We use standard architecture. We do not have to invent any new architecture for our approach. And finally, we develop an effective method for estimating relative weight parameters for our loss function.